Dear students, today we'll continue our practice on Mathematical Analysis 1, and today's topic is increasing and decreasing intervals of function, concave up, concave down, and flex points. So, let me start with the definition of increasing and decreasing functions. Here we have the definition. So, given any x1 and x2 from any interval I, with x1 which is less than x2, if satisfied f of x1 is less than f of x2, then f of x is increasing on I. So it means, for example, if you have any, let's consider any graph here. So, and now, for example, let's take any points x1 here and x2. So in this case, let me write here. So x1, any point, and here, for example, x2, where x2 is greater than x1. And if the graph of this function is, for example, like this, so let me write here, for example, like this, yeah. So here we have f of x1, in this case, and in this case is f of x2, the top of them. So this is f of x2. And now you can see f of x1 is also less than f of x2. And it means this function is increasing on this interval. And now the otherwise x1 and given any x1 and x2 from an interval I with x1 less than x2, let's find this again. But in this case, if f of x1 is greater than f of x2, if it is greater, first one, then f of x is decreasing on I. It will be like inversely in this case. So this is decreasing on I. And now, fact, if the first derivative of f of x is greater than 0 for every x on some interval I, then f of x is increasing on this interval. So again, if derivative is greater than 0, it will be increasing on this interval. If the derivative of this function is less than 0, so it means f of x is decreasing on this interval. If it is equal to 0, it will be constant function in this interval. Okay, now so and now let's consider the first example. Determine all intervals where the following function is increasing or decreasing. You can see here we have function f of x, polynomial function, minus x fifth degree plus 5 over 2x fourth and 40 over 3x cubed plus 5. So what should we do in this case? What should we need to do in this case? So using this fact, here we need to check the derivative of this function. If it is greater, it will be increasing intervals. If it is less than 0, it will be decreasing intervals. So for this, we need to take the derivative here, and after factorizing, we have this one. So it is minus 5x squared, x minus 4, and x plus 2. So now we get this answer, and here we need to put it is to the interval. So for example, in like this, so in fact the intervals of increasing and decreasing. So let me write here. So for example, in this case, it is the where is the points, the critical points are 0, 4, and -2. Equaling to 0, we get the critical points. So here we have uh, so here we have -2. Here we have 0, and for example, here we have 4. So now what we get? If we divide it to intervals, yes. So if you remember, we had the interval method of intervals where when we solve the quadratic inequalities. Yeah. So this is a little close to this one, and here if we check it, so on the right side, for example, if you take 5 and putting to this function, what we get here? So putting to to this derivative, of course, and we have here here it's written, and for example, in this case, it will be f derivative of 5. It is minus uh, 875, and it is less than 0. So here we have minus, and in this case we have plus in the middle from 0 till 4. We get the same one. So look here. So here we have minus, here we have plus, and then after 0 we need it's no changing, because here we have squared. Yeah, second power, it is even power, that's why it will be again plus. And here also you can see when we check it, so it will be 25 if you take -1, for example, and it is positive. So in this case again we have positive value, it is plus. And then here we have uh, minus, because here odd power, that's why it will be changed. So we can see minus, plus, plus, and minus. So it means minus, plus, plus, minus, it means from minus infinity till -2, and from 4 till plus infinity, this is decreasing function, because here we have minus. From -2 till 0, and from 0 till 4, it will be increasing function. And you can see the answer. Yeah, so our answer is correct. Now let's move to the next one. So here we need to again sketch the graph. Now here we need to sketch our graph of our function. So we have increasing and decreasing intervals. They are increasing and decreasing intervals. So now what should we do? We will do draw our graph. So sketch our graph, and here you can see in this interval, so beginning from so from minus infinity till -2, this is decreasing. So we can see here it's decreasing. And now in this case from 4 till plus infinity, this is also decreasing. So from 4 plus infinity, it's also decreasing. So now, and when it's increasing, this is increasing. When here we can see it is decreasing. So from minus infinity, I mean from this part, yeah, this is decreasing part. Here we have decreasing function. In this case it's decreasing, and here also decreasing. And yeah, we can put here, for example, in this case we denote our intervals like this. It is decreasing the narrow to down, so it's also decreasing. And here we have increasing ones, narrow to up, it's increasing. So now in this case we can see here we have decreasing parts, and here we have increasing parts. From -2 till 0 we can see it's increasing now. So here we have increasing part, and from 0 till 4 also increasing, it's also increasing. So this is sketch of this is our graph of function, graph of our function. Okay, now, and here we have the summary. So first derivative test, suppose that x equal to c is a critical point of f of x, then if the derivative at this f of x is greater than 0, so the left of c and the derivative is less than 0, the right of c, then x is of c is a relative maximum. So it means if it moves from if we want to say easily, if it goes from plus to minus, because here if f of x, f derivative of x is greater than 0, it means here we have increasing interval, and we need to put plus here. And if we move from plus to minus, in this case this is maximum point, this is maximum, this is maximum. And when we move from minus till to plus, it is minimum point. It is minimum point. If we have the same sign on both sides of c, it is neither or a relative maximum nor a relative minimum. For example, what we have here, from minus till plus we move. What is it? It is, from our definition, from minus till plus, it is minimum point. If it is from plus to minus, it is maximum point. So in our case, -2, it is minimum point of our function, and the +4, it is maximum point. And we can see in the graph also, so -2, it is minimum point, and the +4, it is maximum point. And we can see it's relative minimum and relative maximum, respectively. Okay, now, the next example, find and classify all the critical points of the following function. Give the intervals where the function is increasing and decreasing. So we have the following function, g of t. So firstly, we need to find all critical points, and to find all critical points, again, we need to find the derivative of this function and equating to 0. We did such kind of operations here, and we have the following function after finding the derivative of our function, after simplifying, of course. And then what we get from this one, if we equate to 0, we have t is critical points are plus minus 2 and plus minus square root of 12 over 5. So plus minus 2, because of here the derivative does not exist, and when derivative doesn't exist, this is also critical point. And the next one is from numerator equating to 0. Okay, now let's put these points to our real line, and what we get here. So it is approximately it will be 1.54 and 9. So here we need to put all critical points here, and what we have, -2, this one, this is -2, and +2, and the next 2 points, yeah, plus minus 12 over 5, square root of 12 over 5. And what we get here, here we have plus, here we have plus, and here we have also plus again, because if we find it, it will be again plus. And in the middle we have minus, and here we have plus, and here also we have plus. So when it's decreasing, when in the middle, yeah, so from minus 12 in this case, so it is decreasing. And when it's increasing, increasing is this this interval, on this interval. So we have increasing function here. And now find maximum and minimum. What is maximum and what is relative minimum and relative maximum? So if you consider this real line, what we get here, this is from plus to move to the minus. So the point minus 12 over 5, it is relative maximum. From plus to minus, this is relative maximum. And 12 over square root of 12 over 5, this is relative minimum, because it goes from minus to plus. It is relative minimum. Okay, now this is graph of our function, and here we have increasing in this part, and in this part we have decreasing one, and here we have again increasing and increasing. So we have 4 critical points and 1 decreasing interval, and 1, 2, 3, 4 increasing intervals, and the point minus 12 square root of 12 over 5, it is this point is maximum point, and this one is minimum point. Okay, next one. Suppose that the elevation above sea level of a root is given by the following function. So this is also the same with the previous one. Here also we need to find firstly derivative of this function, and then yeah, here we have that interval minus 12.5 till 12.5, because it's written if we start 25 miles to the west of the initial point of measurement and drive until we are 25 miles east of the initial point, how many miles of our where we're driving up an incline. So here we have interval, and we need to consider this function on this interval minus 25 and 25, and this is derivative of our function, and equaling to 0 our function, we get the following equation, and after solving this equation we have the following roots, and how many roots we have on this interval, on interval minus 25 and plus 25. Here we have just 4 critical points which are belongs to our interval, and we need to check for these critical points and points of extrema, and so we'll find our extreme points between our critical points, from our critical points. So, and test this one. So we have here plus in this case, and here in this interval minus. This one is again plus, this is minus, and this one is plus. So what we have, the increasing intervals are these intervals, first, third, and fifth one, and the decreasing is second and the fourth one, beginning from the left side. Okay, so now you can see from plus to minus, this is relative maximum. From minus till plus, this is relative minimum. Yes. Okay, now the next section, it is concave up and the concave down of and flex points. So what is concave up. Here we can see the graph of concave up decreasing and the concave up increasing. So we can see this concave instead of concave up and concave down, concave and convexity, concavity and convexity. So they are same. And this is concave down and concave down increasing here. So a function is concave up if it opens up, and the function is concave down if it is opens down. So this is, yeah, obviously here we have open up, that's why it is concave up, and here we have open down, so it is concave down. And note as well that concavity has nothing to do with increasing or decreasing. A function can be concave up and either increasing or decreasing. Similarly, a function can be concave down and either increasing or decreasing. So it's probably not the best way to define concavity by saying which way it opens, since this is a somewhat loose definition. Here is a mathematical definition of concavity. So given the function f of x, definition, given the function f of x, then f of x is concave up an interval I if all of the tangents to the curve on I are below the graph of f of x. And the f of x is concave down on an interval I if all of the tangent to the curve on I are the above graph of f of x. Now we will consider the in graph also this definition, and it will be more clear. So there is one more definition that we need to get out of the way. So definition 2, a point x is c is called an inflection point if the function is continuous at the point, or flex point, yeah, and if the function is continuous at the point and the concavity of the graph changes at that point. So if the concavity changes at this point, we will call inflection point or flex point. So here we can see the graph of this, the illustration of the definition. So if we said here, if all of the tangents to the curve on I are below the graph of f of x, this is concave up. So we can see all tangents are below, so it is concave up. And otherwise, if all tangents are above the graph of f of x, it will be concave down. We can see in this case all tangents are above. So now, fact, given the function f of x, then if the second derivative of f of x greater than 0 for all x in some interval I, then f of x is concave up on this interval. If the second derivative of f of x is less than 0 for all x in some interval I, then f of x is concave down on I. So we can connect concavity with concave up and concave down with derivative. So if now we need to consider the second derivative, not first, second derivative, and if it is greater than 0, it will be concave up. If it is less than 0, it will be concave down. So the first example for concave up and concave down. For the following function, identify the intervals where the function is increasing and decreasing, and the intervals where the function is concave up and concave down, and use this information to sketch the graph. So here, firstly, we need to find increasing and decreasing intervals, and find the intervals of concave up and concave down. Firstly, to find intervals of increasing and decreasing, we need to find what? Yes, of course, we need to find the first derivative of this function. And after factorizing the first derivative, we get this one. So here, critical points are 0, 1, and minus 1. And to find the intervals of the concave up and concave down, we need to find the second derivative from this of this function. So it will be derivative of this function, the derivative of the derivative. So it will be 30x 2x squared minus 1. So if you find here also flex point, so it will be I mean not flex zeros, so it will be just 0, and here we have 1 over 2 square root of plus minus 1 over 2 plus minus square root of 1 over 2. So now let's find firstly the intervals of increasing and decreasing. So here we can see if we put our points, so it is 1, 0, and minus 1. So beginning from right side, it will be plus here, here minus, here also minus, because this is even power and without changing of sign. So minus, and here we have plus. So we get the increasing intervals are from minus infinity till minus 1, and from 1 till plus infinity. This one and this one. Yes. So this is increasing intervals. So they are increasing intervals. So now decreasing intervals are this one and this one. So this is decreasing intervals. And what is maxima and what is minima? In our case, maxima it is point of minus 1, and minima it's point of 1. Relative maxima and relative minima. So now, so we said minus 1 is the relative maximum, and x is 1 is the relative minimum. And x is 0 is neither relative minimum or maximum, because there is no changing of sign. And now, let's find the, we found our second derivative, and zeros of this derivative, it will be 0, and I said plus minus square root of 1 over 2, and this is approximately 0.7. And now we need to check now this second derivative of our function. So this is similarly with the first one. Here just find the signs of in our intervals. So the first one from the right side will be plus, then minus, plus, and minus. The pattern signs we have. And what can we say here? So if it is greater than 0, so if it is greater than 0, it will be concave up. So in this intervals, this one and this one, here we have concave up. You can denote like this. This is concave up. And in this case, in these intervals, we have concave down, because it is minus. If second derivative of function is greater than 0, it will be concave up. If second derivative of this function less than 0, it will be concave down. So we will denote like this. This is concave down. Yes. So we have the intervals of concavity. And now we can see if the signs are so changing, it means if it's changing concavity, if you move from concave up to concave down, or from concave down to concave up, it means from minus till plus, or from plus till minus. We call this kind of points inflection points. Yeah. So these three, 3 points are in, inflection points. And now, using this information, we can draw our graph. So here we have increasing intervals, and on the point 0. So this is inflection point. Here we can see concave up and then concave down. So look here, it is concave up and goes to concave down. Or in this point, so here also we have concave. Firstly, we have concave down and then concave up, concave down and concave up. And in this point also concave, this the last point. Yeah, so plus 1 over square root of 2. Here we have concave down and then concave up. This is concave down and then concave up we have. So now, second derivative test. Suppose that C is a critical point of derivative of at this point C, such that is equal to 0, and that second derivative of f of x is continuous in a region around the point C. Then if it's less than 0, I mean the second derivative at the point C, if it's less than 0, then x, so the point of C is the relative maximum. So we can test here, considering the second derivative also, if it is it relative minimum or relative maximum, if we have second derivative also. So here we need to find the critical point of the first derivative function. And if it is greater than 0, it will be relative minimum. If it is 0, can be relative maximum or relative minimum or neither. So we can check from second derivative relative minimum and relative maximum also. Okay, for example, the first is graph of f of x is x fourth degree. This is parabola, and this graph has a relative minimum at the point x0, because let's check it. So the second derivative of this function is the first derivative is 4x cubed. Yes, 4x cubed, the first derivative, and the second derivative is 12x squared. Yes, I mean the f second. This is f first. This is f first. So now if it is, so this is positive always because it's x squared. Yes, that's why it's positive. So what it means, if it is positive, you can see here from the second condition, if it is positive, it is relative minimum. So it means this point is relative minimum. Because we need to equating 0 and we get 0 here. The next one, minus x fourth degree, which has a relative maximum at x0, because in this case we have minus minus, so minus 12x squared we have here, and this is less than, always less than 0, so it means this is relative maximum from the first condition. If it is less than 0, it will be relative maximum. If it is greater than 0, it will be relative minimum. So finally, there is the graph of f of x cubed, and here in this graph had neither a relative maximum or a relative minimum at the point 0, because if we find the second derivative of this function, the first derivative will be 3x squared and the second will be 6x, and we cannot define in this point the positivity or negative of this function. Okay, next example, use the second derivative test to classify the critical point of the function. So here we need to do the same work with the previous examples and find the second derivative of this function. It will be 60x cubed minus 30x, and finding zeros. So we have three critical points: minus 1, 0, and 1, and then find the values at these points. It will be these ones. So, and what can we say here? The uh, the second derivative of x minus 1 is negative, so by the second derivative test, this critical point is a relative maximum if it is negative, yes. And the second derivative of 1 it's positive, and so we can say it will be relative minimum. In the case of x is 0, the second derivative is 0, and so we cannot use the second derivative test to classify this critical point. And how can you find if we cannot find from the second derivative test? Now we will use the first derivative test to find the it is relative maxima or relative minima. The next example. So for the following function, find the inflection points and use the second derivative test. If possible, to classify the critical points. Also determine the intervals of increasing and decreasing and the intervals of concavity, and sketch the graph of the function. So here we can see the function t times 6 minus t the power of 2 over 3. And now let's find the first derivative. This is first derivative, and the second derivative of this function, and find the critical points. Here we have just the two critical points, 3.6 and t is 6. So now and note as well that we won't be able to use the second derivative test on t is 6 to classify this critical point, since the derivative doesn't exist at this point. So it should be exist. And to classify this, we'll need the increasing decreasing information that we'll get to sketch the graph. So and now we can use for 3.6 the second derivative test, and we have if we put it, we get the negative value minus 1.245, and however it is negative, it will be relative maximum. This is a relative maximum point. And now let's find the number line for the first derivative. and here we have plus, minus, and the plus. So it means we have here plus, minus, and the plus. So 3.6 was the relative maximum. Let's check it. So this is of course relative maximum because it goes from plus to minus. We can find it from the first derivative test also, and now we can define the point 6. So it is relative minimum because it goes from minus to plus. So this is relative minimum point. So now what we have two inflection points again. So because of here we have the derivative of this function is has I mean the second derivative of this function, and it has two uh, zeros, so it is 72 over 10 and 6 again. So it is 6 and 7.2. And now the real line for second derivative, and here we have plus, here we have minus, and here also we have plus. So now what we get here, the concavity only changes as t is 7.2 because from minus till it go so this is also minus. Sorry, here also minus we have. It's minus, not plus. This is minus, and this is minus. So we can see only at the point uh, 7.2 here. Yeah, this is 7.2. This is inflection point for this function because it changed the sign from minus to plus. So this is inflection point, and what we get here, we have concave down, yes, and concave down, and here concave up. You have concave up. And now let's consider the graph. So this 7.2, the point, it is inflection point. It should be here the concave down, and then here we have concave up from beginning from 7.2, and here we have again decreasing function till this point, and then increasing function, and then decreasing function beginning from 6. Yes, the change of concavity at 7.2 is hard to see, but it's just a very subtle change in concavity. We can find it from our equation using the second derivative of our function. So I want to summarize one more time, and here we have two tests. The first one is first derivative test. Let me move it. First derivative test. Here the main idea is if it is moves from plus to minus, it is maximum, relative maximum. If it is from minus to plus, it is relative minimum point. So this is first derivative test, and we have the second derivative test for finding the again relative minimum and relative maximum. Of course, we have concave up and concave down. If the second derivative greater than 0, it will be concave up. If the second derivative less than 0, it will be concave down. And we had if the first derivative greater than 0, it will be just increasing, and if the first derivative less than 0, it will be just decreasing function. And now here we have second derivative test. If second derivative, if we consider the critical point C, and the second derivative of f of x is continuous in a region around C, and if second derivative at this point less than 0, it will be the relative maximum point. If the second derivative at this point greater than 0, it will be relative minimum point. If it is 0, it can be relative maximum. We cannot define in this case. So and this example was the last one for this topic, and we'll continue our next topics. And here we finish our uh, topic, increasing and decreasing intervals of function, concavity, and the flex point. Thank you for attention.